Hi everyone, we are live again on Saturday. So we are here for our online discussion of the Deep Learning book, which we host every Saturday at 11 a.m. I know we're a little bit late today, sorry about that. I am actually at a co-working space with my team today. We're working on our curriculum and learning management system for our upcoming program, which is super exciting. But we are excited to join you again on Saturday for this session. We wanted to give some background information for people that are just joining us. This is a kind of community learning experience that we have. So we think for participants to gain the most experience and understanding of the material covered in this book, we have a volunteer presenter that each week goes through the material in advance and puts together a little presentation for us, which kind of helps us learn and digest all of the information along with them as well, which is really awesome. And especially because we think the best way to learn something is to teach it. We think that this is a really great experience for our presenters who are volunteering. And the presentations can be as short as 10 minutes or as long as an hour, depending on the depth of the material covered. And of course, we do ask our presenters to do slides as well. And if you're interested in being a presenter for a chapter, please sign up on our presenter sign-up form, which is linked in the YouTube page, but also on our meetup group. And our meetup group for this is the AI and deep learning enthusiasts in the Bay Area, and you can find that link as well in the YouTube channel, also on our website, of course, for Excel AI. And we have a returning presenter today. This is Sharif Jazra, who has joined us past for previous chapters and also for part 1 of chapter 11. You want to say hi to everyone, Sharif?
Hi, Laura. Hi, everybody. I'm Sharif. Happy to be back as always and talk more about deep learning and machine learning. Couple things about my background for those who don't know me. I'm a software engineer. I've been in the wireless industry for 11 years and the last 4 focused on machine learning. And just this year I started getting more focused on deep learning. And so I've been going through the book as everybody has been and excited to be presenting. So I'll be kind of continuing over the last part of the chapter on practical methodology. So last week we went through a big portion of it, and so there remains a little bit. So I also want to encourage people to ask questions, as many questions as possible, because that will be more focused on, I think, questions and answer. As a just quick summary, I'll summarize what we went through last time. In the chapter content, we had gone through the performance metrics. We talked about what are the different ways to set the metrics required for achieving a certain level of performance and how to pick them. And so we talked about precision, we talked about recall, talked about the confusion matrix, and then we talked about how to pick a baseline model. So that was important because we need to have something working end-to-end as soon as possible, pipeline end-to-end. And then we had the flow chart going through cases when we would need to gather more data. And that was basically a balancing act between underfitting and overfitting. So we talked a little bit about that last time. And then as we go through that procedure, trying to find the optimum capacity for the network, we talked about selecting hyperparameters and strategies for that. There was 2 main ones: the manual one, that's epitomized in the grid search methodology. And then we also talked about automatic ones, particularly we talked a little bit about the random search, and we talked about the model-based hyperparameter optimization. So if there are any questions about those parts, we can definitely address those. Laura, you can see the questions. I can't. Let me see if I can pull up if there's any questions.
Yep, I've got the chat up. There's no questions yet, but we do definitely encourage our viewers, if you have any questions or want to add to the discussion, that's a big part of this and why we're hosting this online as well. We usually have people who join us from all over the world, so we're really excited to have you guys be part of the discussion.
Okay, so I'll pull up the last section, which was the debugging strategies. So here in this sort of last section of the book, we're figuring out ways to debug what's going wrong with our code, with our model. And so generally there are two difficulties. And the first one is that we don't really know a priori how is the algorithm itself going to work, or how it will behave. So we can't predict that. We don't have sort of a theoretical way to say this is what's going to happen. The second thing is we don't know how submodels, um, we don't know how to identify submodels that are misbehaving, because it's very likely that another module might compensate for misbehavior. As an example that's given, we take the SGD method, but we say that maybe we made an error updating the biases. So this is, let's say, our own implementation of gradient descent. So let's say we make a mistake with the bias update, and we forgot to put the gradient. So we just update the bias by alpha, the learning rate. We forgot the gradient. What happens is that biases will keep on getting more negative. However, there is a likelihood that weights might actually compensate for this effect. And from the outside, from the output, we won't really see, we won't be able to identify that that's the problem, right? So, so even though there is a problem, the network is not performing at optimum capacity, it's not clear from the outside. So we need some more specific method to go through to debug the actual software and improve its performance. So there are some important debugging tests given in the book. And the first one is to visualize the model in action. So that's important. What are we producing? Let's look at the data that you're producing. If you're doing an object detection application, you can superimpose the objects that you've detected in the image itself over the original image. Make sure that they are really matching the area that you've detected over. If you're building a generative speech application, listen to the output audio. Make sure it makes sense and it's clear. It's what you expect. So the thing is that it's important not just to rely on quantitative measures for evaluation. There might be a problem measuring them. And by looking at the output, you have more confidence that what you're measuring quantitatively is matching your actual output. So don't always rely just on quantitative measures. Now, second debugging strategy is to visualize the worst mistakes. So often you have a confidence metrics available for you to use. And for example, the softmax uses output probabilities. So you can use those to evaluate the performance. So one strategy is to look at the training examples that perform worst. So that means that the algorithm is predicting certain examples to be of a category that's the wrong category, but it gives you a high confidence for that. So this happened in one of the application that one of the authors worked on, which is the street numbering labeling problem, and we'll talk a little bit about that in the next section. So sorting the examples in order of most confident mistakes allows you to see why is the labeling incorrect. Like in the previous case, it was a cropping issue. So that's important. That's a strategy for you to see that. The next one is to reason about software using training and test error. For example, if train error is low, but the test error is high, so it's likely that your training procedure works. You're able to sort of fit the training error, the training set, but you might be overfitting, getting a bad test set error or validation set error. So some of the recommendation based on, I guess, the author's previous experience is to make sure your code is properly written for both the test as well as the trained data set. For example, you might make sure that your model is saved properly after you do the training and use the proper updated parameters for the test data set. Or check whether the data set is prepared differently than the training data set. Also, if both errors are high, it's usually difficult to decide whether it's a software bug or an algorithmic problem. So there are there are a couple more debugging strategy that allows us to figure that out. Here I'm using test again. The authors use test, the test data set instead of validation. I think they really mean validation, but I've kept test set here. So the next strategy is to fit a tiny data set. So use, especially if your train error is high, that means you are not able to fit your training data set. So is that a problem with your training algorithm? To find out, you could just take a very small data set and make sure you can at least fit that. So you could even take one sample and make sure that your algorithm is labeling it correctly if it's a classifier. If you have a generative model, at least you can make sure you're reproducing that sample correctly. So you have more confidence here that your training algorithm is working properly. The next strategy is to compare backpropagated derivatives to numerical derivatives. And this especially is true if you are implementing your own backpropagation algorithm. So you are writing the code for the gradient step, and it's often the case you make mistakes writing that code. So how do you test it? And a very common way to do that is to use the method of finite differences. So that comes from math, and we know that the derivative of a function on the left side, by definition, is this this difference of the function at the same point x with a small epsilon difference divided by that same epsilon difference when that small value goes to 0. That's kind of your, by definition, equation for a derivative. And you can say it's almost equal to, instead of just a limit, you use equality, and you use a very small epsilon value to test that and to get the value of the derivative. So you could use that, or you could use the method of center differences, and that might be a little bit more accurate. And so instead of using x plus epsilon and x as the 2 points, you can use the point around x, so x plus half epsilon and x minus half epsilon. So it's important to pick an epsilon value that's large enough not to be rounded by finite precision numerical computation, because if you get into the rounding problem, then the difference might be 0. And so you might not get the value that you want. So it has to be large enough, but then it has to be also small enough so that you get an accurate value of the derivative at that particular point x. The thing with the finite difference method is that it's only for single variable functions. While in neural network, we are usually computing gradients for vectors, so multidimensional. So what do we do in that case? So assume that we're trying to estimate this g function or compute the derivative of it. And it goes from an m-dimensional space to an n-dimensional space. So your input has dimension m, so m input features and an n output values. So one strategy is you could compute your finite difference values for the combination of all input and output values. So you'll get m by n partial derivatives to compute, and that might take a lot of time. So another strategy would be to actually try to reframe the problem in a way that you only have to test a single variable function. And so the idea is to calculate the derivative of a projection of g, because the derivative of its projection should still be correct if you have the correct derivative of g itself. So for example, here is the projection f, and you choose random vector u and v. And as you can see, you're doing a projection at the input, that's v by x, and then you get the j here, and then you do another projection on the output by multiplying it by u. So at the end, you get f, which is a single value, a single output, at least. So it's more efficient to compute. That's the idea, is that you have reduced the amount of computation needed, but you can pick multiple values of x, not just one, and you can make sure that you get the expected values. Okay, and then the third method that's given is using complex number functions. So if you have a numerical computational framework, you can use results from complex function theory, and that will help avoid this cancellation effect due to the subtractions. So by definition, we have that the function of a complex number, x plus I by y, where I is the square root of -1, that can be written as a sum of two functions, a real function u of x and y plus I multiplied by v, which is also a real function. And if you have that decomposition, the results are that a Taylor expansion around point x plus I epsilon will reveal sort of fx plus I epsilon, the derivative of f, with a precision of O of epsilon square. And if you take the imaginary portion of that, as can be seen on the bottom right, you can get the derivative of the function that you're looking for. And again, that's with a precision of epsilon square. So what's good here is that you are not using a difference anymore. You just have to calculate fx plus I epsilon and divide that by epsilon. So with this computational framework, you can get that value and you can avoid that rounding problem. And there's more discussion in it in that Squire and Trapp paper from 1998. And finally, the last strategy that's given is to monitor histograms of activations and gradients. So in particular, look at the pre-activation values of the hidden units and see if they are saturating. For example, if you're using ReLU, make sure, just check how many of those ReLUs are off or just turned off. Your output is 0. And also for how many epoch this is happening. And this gives you a sense of the amount of saturation. Maybe there is some problem with your initializations. For tangent h, tan h, look at the average of the absolute values of these pre-activation. That will also give you information about saturation. Another thing to look at is how quickly the gradients increase or decrease. And we know for deep networks, we have to calculate these gradients over like various levels. And if they move too quickly or then that can negatively affect the learning algorithm itself. So there is suggestion that the magnitude of the changes shouldn't be more than should be around 1% of the parameter values. That's from Botu 2015. So when you're measuring every epoch, you can look at the gradient values and you can compare them to the absolute values of the parameter themselves, and make sure you are changing in the magnitude of 1% of that parameter's value, or not 50%, which is too fast, and not 0.001%, which is too slow. And last suggestion, which is more for algorithm that will be discussed in part 3, sometimes the learning algorithm will have certain guarantees, and then you can check that those guarantees are actually being met from one epoch to the next. So you have more confidence that it's working properly. So summary of the techniques we discussed: visualize the model in action, visualize the worst mistakes, those mistakes where the classifier is very confident but the label is actually incorrect, reason about software using training and test errors, fit a tiny data set. If your training error is too high and you don't know if you have a software bug, make sure you can fit a small data set. If you're implementing your own backpropagation algorithm, compare the values you get with numerical derivatives using the finite difference, using the projection method, or using the complex function method. And then make sure you're not oversaturating or for too long, or your gradients aren't being updated too fast or too slow. So monitor the histograms of activations and gradients. Okay. Wait, if there are any questions on this section, you can wait for a little bit.
Yeah, there are no questions so far. So I'd say let's go ahead and keep going.
Okay. Yeah. So let's do the last section. So the last section is really a summary of this paper or this problem that Goodfellow worked on, which sort of bring together many of the concepts that he talked about in this chapter. And this is the goal of this application is to use Google Maps and Google Street View pictures, and from those extract the building numbers, and then populate Google Maps with the right values. So it's the transcription of Street View address numbers. So that's the link for that paper. So in that section, Goodfellow basically goes through the whole process of designing and implementing and debugging that deep learning model for this application. And so it all starts with data collection, which is a manual process. So cars are going around cities and streets collecting raw images, and then humans are actually labeling them. They are labeling the numbers of the buildings. And so so before you actually get to the deep learning model, there's a lot of pre-processing going for curation. Even some machine learning algorithms are used to detect where in the picture the house numbers are. And so that's an amount of work. He doesn't go into details, but I think it's challenging on its own. So once you have the data, we said in this chapter, we have to pick the performance metric. So which metric to use and what value to aim for. And so in this case, they were really tied to business objective, because maps are really useful if they have very high accuracy. And the goal set was to match human level, which was 98%. And so in the beginning, this goal sacrificed coverage. Coverage, as we said, was how often the machine learning algorithm actually return a response. So when it has high confidence that it has the right answer. So they worked on accuracy, and then later on, coverage became the target of the optimization, which eventually reached 95% as the ConvNet improved. I'll go a little bit through the method. First, what was the baseline that they should use? And so they started with a ConvNet with ReLU as activation function, and then at the output, we basically want to get that sequence of numbers, right? So they use n different softmax as outputs, they're independent, and each one will predict, as together, they will predict the sequence of number. And each one of those softmax was basically trained independently of the other. Now, how do we improve these coverage metrics? So, so like I said, the system, theoretically, coverage is when the system returns, is how often the system returns an actual value. So in this case, it shouldn't classify an output if the sequence probability is too low. It's less than a t for some threshold t. And so the question was how to pick this probability distribution. And initially they chose it to be the product of all softmax probabilities. So just the product, multiply all of them, and you get the output of the probability of the sequence. So they use that to start with, and then as they wanted to improve, they developed a special output layer and a cost function. So coverage improved and until it reached 90%. So then they asked themselves, was the problem underfitting or overfitting? And to know, they had to monitor the training and the test error. And so for them, they were almost identical. They had a lot of data. They had tens of millions of labels. And so they thought that there were two possible causes for this. It could be just underfitting. So it's not getting the best performance on the train set itself. Or there could be some problem with the data. And maybe the quality of the data is not good. There are some problems there. So so they decided to visualize the worst error. So that was one of these techniques that we mentioned earlier. And they visualized the incorrect transcriptions, which had high label confidence. And so what did they find? They basically they found those were actually badly cropped images for the most part. That's an important finding, right? And it basically says that an image of 1849, for example, would be cropped to show 849. And so that label would be detected with high confidence, but because it's cropped, it's just not the right value. So in their pre-processing step, they were kind of they had to determine the width of the cropping region, and they decided as a consequence of this finding to increase that a little bit and expand it so so these cropped image would not appear anymore. And actually that got a lot of good improvement. Coverage was increased by 10 percentage points. So that was a big performance improvement. And then the remaining increase in performance came from tuning hyperparameters. And so that was mostly making the model larger so that you can learn more. So that was a kind of some underfitting, handling some underfitting. And but they kept some restriction on computation, so that it would not take too long a time to train or too long a time to actually do the inference itself. So overall, the project was deemed very successful. They're able to label hundreds of millions of addresses and at faster and lower cost compared to the human effort. So they started with tens of millions of label, and that took a lot of time, obviously, to actually label. But they were able to build high accuracy, high coverage model, and they used that to label many more hundreds of millions of images. And so so through that last section, they basically help us illustrate how to think about a model, how to increase our metrics so that we reach our target, and what techniques they use here, visualizing the worst error. They tune their hyperparameters to increase the model capacity, and as they did all of that, they were able to increase and reach high accuracy and coverage. That's basically.
We do have a question from our chat. So Rabindra has asked, how can we solve underfitting and overfitting problems in a neural network-based architecture?
Okay, so we talked a little bit about this in the previous section. So let's start with the problem itself. Here's a view of capacity versus generalization error. So generalization error is the error on the validation set. So how well we're doing on data that we haven't seen before. And capacity is how well our model can learn. And in one section, we described this capacity as being constrained by three things: the representational capacity of the model, so which is basically how much can the model itself learn, so the number of hidden units, the number of levels, the structure itself. The second one was the ability of the learning algorithm to successfully minimize the cost function. So this is more about training and optimization. So that's not good enough, you're not going to reach high capacity. And the third one was the degree to which we can achieve regularization. So that's important to lowering our generalization error. So these three methods together can help us increase our effective capacity. And so we went through a list of parameters that can be tuned for that purpose. And each of one had, we could change these in a way that increased the capacity. So we had a table for that. So, but the point was that, so as we change the capacity, we can move from a zone of underfitting to a zone of overfitting. And we want to be in that sweet middle spot where we have optimal capacity. So so where the generalization gap is smallest. We talked a little bit about how to achieve that, how to change these hyperparameters. Capacity increase with the number of units, with the weight decay coefficient. And also we had a table here. We talked a lot about the learning rate. That's one of the most important hyperparameters to reduce, to get to that sweet spot. If you don't have anything, you don't have time, and that's the only thing that you can do, just focus on the learning rate and get that right. And here it shows us that that the learning rate has a U-shape as a function, like the training error has a function of has a U-shaped function in terms of the learning rate. If the learning rate is too high, then the gradient descent step will be too large and will be bouncing back around that optimal, that minima, that local minima we're looking for. And if it's too low, we might go just too slowly, and we might get stuck in other minima on our way to that, on our way to minimizing the error. So we have to find that learning rate that's right in the middle. So you have to basically tune it. You have to try multiple values. In general, if the training error is too high, you might consider increasing capacity. If you're not using regularization, but you're confident that your optimization algorithm is correct, then maybe add more layers, add more hidden units. That's how you increase your capacity. So it's always something to do with the training and the validation set. So monitor the error on these two to decide how well you're doing. If your value on the training set is too large, you're underfitting. You should do better. You should be able to go down a long way. You should be able to overfit actually the training set technically. But on your way, if your validation set error is going down, that's good. If at some point it starts going up, then you've reached that past that point, and here your generalization error is starting to get worse. And so you should think about generalization, regularization techniques to use. And so generally when you start using regularization, your training error goes a little bit down as well. Sorry, it goes up. You do worse on your training set. But what you want to make sure is that your gap is shrinking with some acceptable training error. So, so the error can be written as a sum of a train error plus the gap. And so obviously we want the training error to remain low, but we also want to make sure the gap is low. And so as we decrease, we want to make sure that the validation error decreases faster than the training error increases. So, so here regularization techniques are like adding dropout, and different value of the dropout rate, or doing the changing the weight decay for the layer 2 norm parameter regularization, you can change that. So you can make it bigger so that the parameters magnitude are smaller. So there's less range of change for them.
So we have another comment by Roberta. He says, if the learning rate is gradually increasing in training time, that means the model is learning correctly. Can you confirm that?
Can you repeat? Let me see. If learning rate is gradually increasing
in training time, that means the model is learning correctly. Can you confirm that?
Do you mean to say that the error is increasing, or the I'm not sure I'm clear about the question. Typically, so there are techniques for the learning rate, for changing the learning rate itself, and so that it's not always at this high value as you are doing your gradient descent. So we talked about 3 strategies. Let me bring that up. Let's see where. I'm not trying to find my slides. So there are basically 3 ways. One is to decay linearly your learning rate until you reach a fixed minimum. So the thing with the learning rate, as you are getting better, as you are getting close to your minimum, you might consider reducing the learning rate as you get closer, so that you don't bounce over it. So there are decaying methods for the linear rate itself. One of them is this linear decay until you reach a fixed minimum, or you could use an exponential decay, so the value exponentially decreases. And the third one is decreasing the rate by a factor of 2 to 10 when the validation error itself plateaus. So there are various techniques of changing the values of the learning rate as you are as your number of epoch increases. I don't know if does that answer the question?
He says, how could we ensure that our model is learning perfectly at the training time?
Well, you have to, so perfectly is the trick kind of word. And you have to make sure your errors are decreasing, right? So you might have set a target previously, and you talked a little bit about that. What should your accuracy be? What should your precision and recall values be? And so as you perform one training, one SGD training with your hyperparameters, you are getting those metrics. If they're not good enough, then you have to tune your hyperparameters to try to get a better value. So it's this back and forth. It's this iterative process. That's the way you make sure you reach your the best performance. So you can't say in absolute this is the best thing. You can only set targets and then say you've met those.
I think that makes sense. So a question that I actually have, so for the last example that you reviewed, that was done by the author, how specifically does this differ from, for example, the MNIST data set that was done and is a common problem used in machine learning and has been also updated for deep learning? Can you describe that a little bit?
I think the MNIST was first one letter at a time. It was very nicely curated data set, so it has this fixed it has a fixed width and height for the letters, and so you don't have to do any pre-processing. It's given to you, and it's just one letter, so it's the simplest kind of image recognition for letter recognition. In this case, we have we're basically taking pictures of buildings, which has the building number in them, and just using that picture, we want to get the values in the building number itself. So so you have to first get the right cropped part of the image which has the numbers. So that's one. That's a challenge in of itself. And then it's multiple numbers with all these different fonts, this different ordering, the largeness, the smallness of the number, the coloring, all that differs. I don't know if MNIST has that all that variation in their data set.
I think there's newer versions that have some variation, but definitely the original was pretty straightforward.
Okay, yeah. So so I think it's and they have tens of millions of data points, so they can really I mean, it's much more than MNIST, so they have the ability to generalize much better if they train on their data set.
Definitely.
What else they say?
And we'll ask the audience if there are any other questions in the chat or if they want to add to the discussion to go ahead and do that now. We're getting close on time, so we'll be wrapping it up soon. We want to give the opportunity for anyone to ask questions they might have. Okay, we have another question in the chat. For ensuring better robustness and handling sparsity, how much does a model depend on the quality of training data at the testing time?
The quality of the data, I think, is always a big problem. If you don't have good data, you're not going to get a good training model. And actually, you will see that in your training data set, if you are not able to, if you have a mix of good and bad data in your data set, and you're not able to overfit that training data, assuming that you have a good optimization, I'm very confident about that, but still you can't get, you can't overfit. It's not the amount of data that's problematic. You don't need to gather more data. You need to look at the quality of the data. Like in this case, they had problems with the cropped images, and so that's bad data. They're able to find out about those by visualizing the worst mistakes. So that's one thing to try and make sure when is your algorithm performing the worst, which is when is it classifying with the highest confidence around class. And I would suggest, you know, in the beginning, especially making sure that you have high quality data. So it will eventually depend on the performance metric that you're using. If you want to reach very high accuracy with bad data, that's not going to happen, very likely. You want to, like here, they want to match 98% human accuracy. And they have high coverage, 95%. So can you reach that with bad quality of data? I mean, that depends. Maybe there's something about the problems that that makes it more where the kinds of mistakes are not as important. But here, cropping is obviously a big mistake. Like you can crop the number in the middle, you're not going to recover from that. So yeah, it depends, I guess, on the kind of application at some point, and then it depends on how good you want your algorithm and how good you want your performance to be.
Okay, we have another question. If I see that the model is not improving at the training time, what should I do?
We had some suggestions here. Let me pull it up. I think this will. This is a nice picture from the book. I kind of made it into a flowchart. Assuming you have an end-to-end working pipeline and some performance metric and the target value you want to reach, you do first start by looking at your training set performance. If that's performing poorly, if that's your question, you want to see whether you can improve. So you may be in the underfitting zone. Sorry. Or your training algorithm itself might have some problem. Maybe the learning rate is not good. So you could start by tuning that learning rate a little bit. Or it might be that you're underfitting because the model is not large enough. So you might increase the size of the model, like add more units, more hidden units, more layers. That increases the representational capacity of the model. And then if that's still not working, they suggest looking at the quality of the data. That's what we talked about just now. Is the data too noisy? Maybe you have the wrong input. Maybe the input you have don't correlate properly with the output so that the function that you're learning is not good enough. And so the suggestion is to collect cleaner data and then to start again. If your data is not good enough in terms of quality, you're not going to do better at the performance. So this mix of suggestion here, make sure you have back propagation is working properly. Make sure you've tuned somehow the learning algorithm so that it reaches some acceptable training performance, training set error, low training set error, or increase the capacity of your model so that you don't underfit. So you can also try using to just make sure your training algorithm is working properly. You can try using a tiny data set, so a subset of the training set, even maybe 1 point, and just train over that and make sure you can overfit. On that training set. So that gives you confidence that at least your training algorithm is working properly. And then so you have to repeat. You have to try to go through these various steps until you get some acceptable training set value, and then you can start comparing that with your validation set performance. So in the validation set performance here, if you have a good training set but a poor validation set performance, if you can get more data, that's always good. Get more data if you don't have enough data. So that should help you do better at generalizing. Here we are in the zone of whether we're overfitting or not. The gap might be large between the training and the validation set, and that might be because you're overfitting. So maybe so improve regularization, add dropout, maybe use a larger, or sorry, smaller weight decay coefficient, or generally reduce the size of the model. So that also helps achieve a better generalization. And again, they stress that getting more data is always good. So if still the gap is not shrinking, you can get more data and then repeat this this process. So and then also make sure that your training set still maintains a low error. So you have to maintain. We talked a little bit about how we broke down the error as the sum of the train error plus the gap between the train and the validation set. So you want to keep that train error small, and you want to keep that gap. You want to drive the gap down. So so always monitor the two at the same time. And I mean, there's no like final recipe for doing it. So it's these are kind of steps to try, and tuning the hyperparameters, and there are different things to do whether you're in the underfitting or the overfitting zone, and so you have to try all of these things together.
Okay, so last question we're going to take today. At the time of computing error, if the output level is more than 10,000 or even bigger, the output probability distribution passing through softmax layer, is it meaningful?
Okay, let me just look at that. If the output level is more than 10,000 or even bigger, The output probability distribution passing through softmax layer is meaningful. Oh, I think maybe the question is if the value of the pre-activation is very high, and then you take it through softmax, and then you get a very high value. If that's the question, I mean, I don't think there is a. I mean, the probability the softmax itself. The goal of that is to allow you to distinguish between the different labels, and then have use a distance measure to compare to the true labels. So you use the output of the probability distribution, and the output of softmax, and and then you subtract from that the real value. So you want to minimize that distance. So it could be that you get a very high value for one label, and that just shows your network is highly confident. But maybe one problem that could be is that you might start with your initialization parameters at that spot with very high values for one label, but actually the true value is some other label, and so you have to allow your network to drop that value fast enough so that it matches, so that you get the right label value increasing, and then it gets increased faster. So maybe initialization of the parameters and the tuning, that will all affect, that will all determine whether what you're getting is problematic or not. So you say keyword extraction from tweet. I think whatever this sounds like the question would be applicable to any kind of problem. Or unless you mean, is the output level, does that mean the output dimension?
There's a slight delay between the video and the chat. So we'll give them a moment.
Perhaps if you're thinking about, like, for example, the vocabulary of word as output, and whether that's meaningful, there are strategies to deal with that. And I think we talked about, I don't know if you talked about that. Yes, okay. I think in the next chapter, maybe there is a little bit about NLP. And so there are ways to maximize your output function without having to use a softmax with the full vocabulary. In that technique, what we're doing is basically using a binary classifier, and then we basically we have a minimization of the difference. Sorry, we have first a binary classifier. We want that we want the value on that to be high to tell us that yes, this is the right label, and then we want to maximize the distance between this label and a subset of other labels. You can pick, let's say, 10 other labels, and you want the distance between the value for that label and all these other labels to be large. So so this helps you to escape the use of softmax for NLP, for text, and it actually works pretty well. There are a lot of papers that shows the paper that described this in particular. I can post that on the so that you can look at it. But definitely there's a way to deal with that.
Thank you, Sharif. So that should be the last question that we take. We want to thank everyone for joining us today, and thank you for your time, of course, as a presenter, for reading the material ahead of time and putting together the presentation. So just a last review for anyone that's joining us at the tail end of this video chat. This is for the AI and deep learning enthusiasts. We are covering an online discussion of the deep learning book. We do this weekly, Saturdays at 11 a.m. And we do have a presenter sign-up form for anyone that's interested in being a presenter. We do think that the best way to learn is to teach others. So reading the material first, and then putting together a little presentation and getting online with us. Also, we do the same session in person in San Francisco on Mondays, which is super exciting. It's a little bit more lively discussion to have everyone in a room kind of going over the material all together, asking questions and adding to the discussion. So if you'd like to join us on Mondays, that's at Sandbox Suites. You can find the details for that as well on our meetup page, and that's for the AI and deep learning enthusiasts. It's linked in our YouTube. We also have a larger workshop coming up that we've been hosting. We've hosted it here a couple times in the Bay Area. We also hosted it in Oslo as well, in Norway, because we're trying to do those globally, which is super exciting. And those are the Demystifying Deep Learning and AI workshops. And in those workshops, we run parallel sessions for intro and advanced sessions. So we allow people to self-select into those different sessions depending on their current background and experience level. You're not required to have any prior experience in AI, deep learning, or engineering to attend. Really, it's kind of what the title says. We're trying to demystify deep learning and AI. And Sharif will also be joining us as a presenter for that workshop, which is very exciting. So thank you for that. And we do have a really nice lineup of other speakers as well. Everyone from OpenAI. We have people from Stanford, from Berkeley. So it's really great. We really hope you can join us. And if you do identify as an underrepresented person in tech, we do offer major discounts. So feel free to get in touch with us to see if you qualify for those discounts as well. So thank you, Sharif, for joining us and putting this together.
Thank you, Laura, and thank you everyone for the questions and for kind of coming together to understand the material better and sort of moving ahead in this deep learning. And I hope everybody also considers coming to the Demystifying conference as well. I think it will be a very great opportunity for learning. Thank you.
Yes, definitely. Yes, and those will also be live streamed on our YouTube. If you can't join us in person, we would like you to join us online. So thanks everyone again, and we will see you next week. Have a good day.